Good evening. I don't see many people here, but I might as well just get started. So if you did watch the video from yesterday, I did mess up here and I apologize. Do you have any questions about this exercise? So this was the beginning of inference. I went through and discussed each of these bullet points. These are the things you need to know for the final exam. So we talked about the binomial distribution and the sampling distribution of the count. We talked about the sampling distribution of the sample proportion and the sampling distribution of the mean. And then we got to inference. And I gave you a general idea of what we're going to begin with. And it's going to be the first column here that is about confidence intervals. So confidence intervals provide an estimate of the parameter, not knowing the parameter. We begin with the population or true proportion and use the rule. I'll rewrite this because this does appear messy. I'll rewrite this. So in general, we want to use the x bar plus or minus 2 standard deviations idea. Something like that. And I'm going to be more precise now. And I'm going to say, well, you can put your point estimate here. So just like we did x bar, and then we're going to go add and subtract. So within, or you can say give or take. And rather than just saying 2 or 3 standard deviations, I'm going to refer to Z star standard deviation. Oh, I won't write it, but it's known as the critical value. And it corresponds to the C% level confidence. So I showed you that if we wanted 98% confidence, you have to find out where is the Z that puts 98% in the middle. That's what Z star is. That's the critical value. And then you multiply by a measure of the standard deviation. So that's the sample standard deviation. We're going to use a measure of the standard deviation. Now, sometimes we're not going to have the actual standard deviation. In this case, we don't have P, so we can't really put the standard deviation together. We can't calculate it. So in those instances, the more general term for the standard deviation is the standard error. Now this comes from the theory up here. We're going to use the theory we derived that P hat has a mean in repeated samples of P and a standard deviation of P1 minus P over n square root. So that's what gives us this result, but we don't have P. So we use our best guess of P hat instead. And because we can't calculate the true proportions, because we don't have the true proportion, we cannot calculate the actual standard deviation. We call this the standard error. So I did this exercise already. And you'll notice in this first column, these are all confidence intervals. This one is the confidence interval for the proportion, the true proportion, where it's unknown. This one is inference on the true mean, where sigma is known. And this allows us to make also a confidence interval, x bar plus or minus c star times the standard error. It is the standard deviation of x bar from the theory that we talked about, we derived last class. From the theory, x bar has a mean mu and a standard deviation of this symbol. So I'm going to use that as my standard error or standard deviation. And then finally, this is inference on mu, but what if sigma is not known? So this is the most realistic we're going to get. Why would we estimate mu if we knew it? Why would we estimate sigma if we knew it? Or why, how would we know sigma but not know mu? So this is a more realistic, that we don't know either of them. And so it's still the same format, x bar plus or minus the critical value times the standard error, but because I don't have sigma, I use S in its place. S is the unbiased estimator of sigma. So I put S in its place, but I have to pay a price for that. Rather than using the Z distribution, I use the T distribution. So rather than Z star, I'm going to find T star. So I want to look at the T distribution to start, but then I'm going to go back to this row here because we actually used it in the exercise. Over here. Notice the critical values have 3 decimal places. Meanwhile, the Z table only gives 2 decimal places for the Z-score. So where do these come from? These come from the T distribution, and I'll talk more about that tomorrow at the beginning of class, if not today. This is the T distribution. It looks familiar. It looks like Z. The center is also at 0, but the difference is, although it's symmetric, it turns out that the T distribution has thicker tails, so it allows for more proportion in the tails. In other words, you're going to end up with more outliers and more data in the tails. The thing is, though, T depends on the sample size. T depends on the sample size. So it turns out that, remember our discussion of degrees of freedom earlier on. Degrees of freedom is equal to n minus 1. Or degrees of freedom are equal to the sample size minus 1. So you have to have at least 2 observations to create a T distribution. So this is n of 2, degrees of freedom 1. This entire row is what you have to describe the T distribution with 1 degree of freedom. And that's it. This entire row is what you have to describe the T distribution with 2 degrees of freedom. And that's it. And notice they're only positives, but 0 is in the middle. So it's only giving you this half of the distribution. And you're told here that P is the upper tail. So P is along the top here. And inside you have the T-scores. That's the opposite of the Z table. In the Z table, you have the left probabilities inside. And on the margins, you have the z-score, so it's reverse. But this is a very easy table to use, and what I'm going to say just for now is that as the degrees of freedom increase, this distribution begins to look more and more like Z. So let's say that's like, you know, a T. I'll erase that. So let's say that's a T5 or something like that. And then as you increase T, not T, sorry, if you increase this sample size, this gets peakier. It begins to peak, it's tighter. So this will be, let's say, T20. And what happens is, as the sample size increases, the degrees of freedom will increase. So I'm going to go down, and what you see at the bottom is a convergence of these values. So at 1,000, here's 1,000 degrees of freedom. Notice that the last row, or the second last row, are Z values for the tail probability on the right. And they're very close to the 1,000, you notice? So essentially, the T distribution becomes the Z distribution for large sample sizes. So in our exercise, we had we're not going to look at the sample size, right? We don't have that issue at all. We're not going to use T in our example. In our example, we actually had been talking about P hat, and we need Z star, and we use the Z table to get it. But it can also be useful to realize that you can pull it from the bottom here. Oh, what's that? Oh, it's a pointer. So you can pull it from the bottom here for different levels of confidence. So 98% is the one that we were talking about. So for 98% confidence, the critical value is 2.236. So that is exactly what we have in the options. Okay, so we'll talk more about the T-table later. I just wanted to show you at the bottom of the T-table, you can find a few critical values that can you can refer to and quickly solve your problems for confidence intervals. Okay, so then that's where that number comes from, 2.326. I never did notice before that these are the same. I must have edited something and not noticed that I did that. Anyway, this is the best answer. So I'm done talking about confidence intervals for the proportion for now, and I'm going to move on to the next column. Does anybody have any questions about what I did here? Moving on to the next column in the formula sheet. Okay, so here is the next column of the formula sheet. It's a formula that helps you answer questions like, compute the sample size required to obtain an estimate of P within a certain margin of error M, or within a certain width 2M, with C% level of confidence. So that's a lot of general information for what you want to do. What we're going to do is take this expression Is my background noise too much? I have a window open. Let me know. Don't worry, Nivette. All right, so this is the general form of confidence interval. And for our case, we're talking about P, so it's P hat plus or minus Z star P hat 1 minus P hat over N square root. And I want to encourage you to problem solve. I know your test and your final exam are open book, but it's a lot of material that you need to sort through. It's actually not a lot, it's just you need to sort through it, because I'm just kind of repeating the same things, but you got to be clear about what goes where, all right? So you need to practice. You can't expect to get this just with my answer keys on the test day. So I encourage you to try the exercises in advance. All right, so we're gonna give this a new name, or a special name. We're gonna call this the margin of error. You know what a margin is? Marginal, on the road. It's on the side. It's on both sides of the road, right? You have the margin. So that's the idea. This is plus or minus, so it goes on both sides. This is the margin of error. So what I'm going to do is give that a label. That's what's here. So M is a symbol for margin of error. And what we want to do is we want to figure out the sample size that we should draw to obtain a certain amount of precision in our estimate. Isn't this great that we can do this? So let's see. What should that formula be? Now we could just use this form of the expression and plug things in, but we have algebra, so we can algebraically isolate for n. What I'm going to do is move all of this over here. No. All right. So what I'm going to do is use this expression for the margin of error to isolate n. To do that, I take m over z star, and that's equal to square root p hat 1 minus p hat over n. That's an n. And then I need to square both sides. And then cross multiply. So that brings n here, and I inverse this. And that's my formula. That's the formula for the appropriate, the sample size, based on some specifications of the margin of error. So Z star, we know how to get that, provided that the level of confidence, the proportion of observations it wants to capture in the interval. So you'll know that. You'll be able to get the Z star. M is given. And then what is P hat? So this is the discussion we're going to carry out next. I don't know if you had ever seen the Mazda commercials. I call this the zoom zoom formula because it helps you remember that it's Z over M squared. It's very common for students to forget this squared even when they're copying the formula from a formula sheet. So zoom zoom. So P star. So there's several scenarios. Remember that this is about taking a sample. Presumably I don't have one. I've never done this before, so I don't have an idea of what P could be. I want to estimate P. So how could I, in trying to estimate P, already have an estimate of P? That's bizarre. So there's three scenarios I want to review. Someone could tell you what P is, and you could use that as your P. I've replaced it with P star rather than P hat because that is misleading, as though, I have a sample to calculate P hat, but I don't. I'm looking at getting the sample size first. So in the first case, let's say someone tells us what P star is, so we can just use that. Case 2 would be if there's no P given, but you have some information from a simple random sample somebody took before. You have some literature or some associate in the industry took a sample before and you know about it, and you can use their estimate of P hat. Provided it's not 0.5, you could use their specific version. Otherwise, if you have absolutely no information, something someone gave you or something someone you found in another sample, you would have to use 50%. That's a midway between all the possibilities for P if you have no prior information. Okay, so it's either use what you're given, use something, an estimate from another sample, or if you have nothing, use 50%. Those are the three cases. So with that, I ask you to use the formula to answer this question. I'll leave you 5 minutes to try on your own, and then I will help you. So I'm going to just leave the cases up and the question. Hopefully you can see that. How'd it go? What'd you get? Did you finish? No answer? Uh-oh. What happened? I'm getting a warning. Are you guys getting a buffering? I'm getting some sort of warnings. Are you there? I don't know how to fix this. Oh, stream current bitrate. Are you there? Is it buffering? Okay, well, I'm just gonna speak. All right. So, suppose we wish to estimate the proportion of Canadians who actually understand the Constitution. What is the approximate number of Canadians who need to be sampled so that 95% confidence interval has a width of 2 percentage points? If width is 2%, then M is 1%, right? Because width is 2 times M. So I have the 95% confidence interval can be obtained from, I can go to the bottom of this chart, or I can find it. Let's just keep finding it for now. So if I want the 95% confidence interval, I need a critical value so that 95% is in the middle. So that puts 2.5% out here and 2.5% out here. So I look for 2.5% inside the table. It's right here. That's 1.96 negative. So the critical values are negative 1.96 and 1.96. I'll show you that is also the same for here on the t-table at the bottom with the 0. 95% is here. So 1.96. Let me know about the buffering. What is going on? I'm getting messages. Well, so this is Z star is equal to 1.96. M is equal to 1%. And now P star. Is there any information about P provided in this explanation, in this question? No, there is not. So when there's no information, you use P star equals 50%. So these are our 3 nuggets of information. So we can solve. Just be careful not to mistranscribing something. 1.96 over, you can write 0.01 squared, 0.5, 1 minus 0.5. And you put it all together, what do you get? All right. So 1.96 divided by 0.01 squared times 0.5 times 0.5. It's 9,604. So the best answer is this one. So the best answer is this one. And because it's closer, no, the logic is when it comes to sample size estimates, you always round up. So in your choice between these two, you go up to 10,000. What if your options were even if your options are these, you should select the one that rounds up. Why? Because the larger the sample size, the smaller the margin of error, right? If you go back, where did we begin? We began here, and then we manipulated this expression So the larger the sample size, the smaller the m, everything else the same. So in that case, I want to maintain my margin within a width of 2 or a margin of 1. I don't want to go beyond it. I don't want to exceed it. That's my goal. So if I go for the larger sample size, I'll maintain my goal, as opposed to if I go for the smaller one and then it underestimates or it makes my margin too high. So I go with, even though 99,600 is closer, I still go with this one. So we round all the way up, or we round to the higher option. I don't know if that makes sense, but hopefully in this example it does. So select the closest option that is higher. So the closest option that is higher, that's not this one. This is close, but this is the closest option that's higher, or greater, or larger. Okay? So that's an example of the second formula in the row. Okay? And that brings us to the third row, third column, right here. Notice, for inference on P unknown, there is no P in any of these types of problems. For the confidence interval problem, we use P hat in place of P. In the sample size estimation problem, we say P star. And over here, there is no P. There's a P hat, which we know is the sample proportion, and then there's this P0. So we're going to talk about first what is going on here, and then what is P0. So where P hat is the sample estimate, what are we doing to P? We're subtracting it by P0 and then dividing it by this thing that looks like the standard deviation, but P0 is inside. So what we're doing actually is standardizing. Or let me write it in words to avoid confusion. Let me write it in words. So Z is equal to your point estimate, so your sample result or your statistic, minus its mean divided by its standard deviation. This is standardizing. So this is taking the statistic that you get, so getting the sample result, and then standardizing it to say what? To say, well, how far is this? It should be how far is this from its mean. So why is this the mean? What we're doing is we're going to try and estimate P. That's what this is, inference. It's your best guess of P. So in order to proceed with inference, because all I've done here is I've made an estimate of P, so that's good. That's kind of inference, right? With an interval. And here I get the sample size I need to get the estimate of P. And then here, so this should be done before this, but and here what I'm doing is I'm going to see if the p-hat gives me any new information. If the sample result gives me any new information that differs from what is currently known. What is the status quo, in other words? So what we're going to do, this is known as hypothesis testing. Or tests of significance. Okay, so this whole column is all about tests of significance. And it's really the last technique I'm going to teach you. Now I'm going to use this tool in different contexts for different statistics, different parameters, but this is the last real new thing I'm teaching you. The rest it's just going to be some variation on what you've already learned. Okay? So let's go to the examples and it'll bring to life what this is all about. So I'm going to teach you how to solve problems of tests of significance in general approach. And then you'll see in the exercises and the homework, you're going to answer parts of the general answer that I'm going to give. So we begin with a random sample of 900 individuals selected from a large population. It was found that 180 regular users are regular users of vitamins. So what I see here is this is my N. And this is, I guess, this is my sample count of 180 vitamin users. And then it explains that we want to test the suspicion that less than 25% of people use vitamins. So implicit in that is a hypothesis test. So I'll tell you, in general, I'm going to use the approach I call HAPSI. And each letter stands for one of the steps. So there are 5 steps. The first step is H for hypothesis or hypotheses. We're going to have a null hypothesis and an alternative hypothesis. And this is how I write it every time. I put the parameter here because I'm hypothesizing about the parameter, in this case P. So it's going to be P and P, an equal sign here, and whatever number I put here for the null, I put the same number over here for the alternative. Now the alternative, well, let's say the null, we'll begin there, is the status quo. What people believe to be true. Like nothing new, nothing special, just it's the status quo. What people believe to be true. Given prior experience, given other data sets, given other research in different countries, whatever it is. So let's say in this population of interest, we want to test the suspicion that less than 25% of people use vitamins. The way I'm showing you to do this, in the null, you can only put an equal sign. So the only thing I can test is the suspicion against 25%. Because whatever I put here, I also put above. And this one has to be an equal sign. So the status quo belief will be that people use, 25% of people use vitamins regularly. And we're going to test that they don't. Now my options here are either not equals would be no difference. Less than would be, less than. Or greater than. So I picked less than. So that was my choice. All the rest, actually, let me put it in red. That's your actual, you get to choose, the problem that you want to pursue or solve gets reflected here. So that's the null, and the alternative is what we believe to be true if we reject the null. Okay, so we put it there. Now here, this number we're going to call P0. In other words, the null hypothesis. So null, this 0 here, or not. So this is null, or not, or nothing. Nada. Nothing special, nothing new, nothing to see here. So the P null, P not, is this value. that's the first step. Second step. The second step is the A step. A for, well, the first A, assume. What shall we assume? Well, to assess or to assess whether our sample corresponds with this status quo, we have to begin by assuming the status quo is true. Otherwise, we have nothing to compare it to. We have nothing to go on. Okay, so we're going to assume H naught is true. If H naught is true, then P is equal to P0 is equal to 25%. And what does that do for us? From the theory of number 2 on the formula sheet, from this theory, we know that the sample proportion has a mean P and a standard deviation P times 1 minus P over n square root. So what we're going to do, we're going to assume H naught is true, and this is true, so that then P hat is approximately normal with a mean of P naught, because I've assumed H naught true, so P will be P naught. And the standard deviation is equal to P0, 1 minus P0 over n square root. So even though on that formula sheet, on that row, I don't know P, because that's what I'm trying to do, infer it, for an instant, I assume I know it. And that's here. I assume I know it, and I use it to compare my result, my statistic to. What is my statistic anyway? My statistic will be P hat X over N. All right, we'll do that in a moment in the next step. But right now, what we have to do is simplify this so that P hat is approximately normal with a mean of 0.25 and a standard deviation if you plug that in. .25 times 0.75 divided by 900 equals square root. So you should practice punching that in to be clear how to do that on your whatever calculator you're using. Okay? Next step. Now we're going to assess the evidence. What's the evidence? The evidence from the sample. Does it correspond to what we've assumed to be true? So assess the evidence, which is P hat equals X over N, which is 180 over 900, which is 0.2. So this is it. Is 0.2 or 20% different from 25%? If not, we would fail to reject the null hypothesis and say 25% is fine. If it is low, it kind of looks low, then we would reject the null hypothesis in favor of the alternative that we have some evidence to suggest that the proportion of vitamin users is less than 25%. In fact, it looks like 20%. So I don't know which one it is because I don't know what 20% really, like, I don't know if that's high or low. In statistics, remember what statistics is about averages and relative measures, and it tells us, it divides data up. This is high, this is low, this is extreme, this is an outlier, and this is close enough. So we need to assess using our statistical tools and our theory, is 20% different from 25%, or is it less than 25%? So that's what we're going to do next. How do we assess? Column number 3. Z is equal to p hat minus p0 divided by this thing. Now we already calculated this, so I'm just writing it to write it, I guess. But we already calculated this above. We're going to basically standardize, taking the mean off and the standard deviation of p hat, which we assume would be that. All right, so let's do it. Let's make the calculation. So z is 0.2 minus 0.25 divide 0.0144. And what do you get? So you find out that this statistic implies that our sample result is an outlier. It's 3.47 standard deviations below the mean. So for us, that's far, right? That's significant. That's bizarre and unusual, given the fact that it should have been 25%, given the assumption we made about what the standard deviation is of p hat and how it should spread out. This implies that it's too far away. So now something's wrong. Is something wrong with my sample, or is something wrong with my assumption? Well, I'm going to assume that nothing's wrong with my sample. I did that correctly. Something must be wrong with the assumption. So I'm going to end up rejecting that assumption in favor of the fact that we have something to report, something new, something bizarre, something. The test is significant. That's how we're going to conclude. Now, I'm not done. I've only done 3 steps. So what I do next is a convention in statistics that, since I graduated with my statistics degree, has been much more popularized, that you calculate what's called a p-value. So you convert this test statistic, this is my test statistic, I'll call it, or more precisely, it's a z-stat. And I convert it into a probability. And we know how to do that, right? We know how to turn a standardized score into a probability. But what probability do I want? I'm going to convert it into a p-value. The p-value is the probability of seeing a z-stat as extreme or more extreme given H0 is true. What am I talking about? So I've written it in symbols, statistics symbols, throughout the notes, but you can just draw a picture of what I'm saying, and that's what I prefer you to do. So when I'm talking about extreme, now notice we never used this in our whole analysis up to the 4th step. Now we're going to use it. So this gets used in the 4th step. I'm talking about extreme. I'm talking about being over here on the left side. Extreme in the left sense from the z-stat. What's that probability? What's the chance of being out here? That's the probability that I want. What does that tell me? That tells me the chance of seeing a Z statistic like that. So what's the probability of seeing that? Now I have to go to the Z table to see that, or use Excel. Or if you guys have figured out how to do this on your calculator, that's good too. So I'm going to go to the tables and look for negative 3.47. And here it is, negative 3.47. So the answer is 0.0003. This is buffering, isn't it? Is my voice buffering? It says we have a healthy stream. Okay, we've had a healthy stream for about half an hour. It just looks like it's buffering to me. How is your stream? Are you guys there? You're so quiet. Text me. Chat with me a bit. Do you have power? Okay, thank you. All right, so let's take that value back. So we got that the chance of being out here is 0.0003 or 0.03%. So it's very small, but we already knew that. We already knew from this step that our result is an outlier. And it's an outlier to the left. It's an extreme value. I just converted it into a p-value because this is important for reporting in statistics. People reading statistics will just look at the p-value, and I'm going to teach you, if you don't know, how to do that. Okay, so I'm going to show you now, and then you're going to see it many times. So the final step is to conclude about what we found. Make a final concluding statement every single time you write p-value less than or equal to alpha means reject H naught. What is alpha? This is called the level of significance. When I say that the Z statistic is an outlier, it's far away, and I refer to the probability of being that far out given the assumption about the proportion, I'm saying that its chance is 0.03%, and I'm saying it's small. I'm suggesting to you it's small. But how small is that? How unusual really is that? I need to set a standard. In statistics, they set a standard for what is unusual. So anything with less than a 5% chance of appearing, and it appears, is considered bizarre. Okay, usually a 5% level is used, but in more conservative studies, when they when they want to be more strict about rejecting the null hypothesis, rejecting the assumption, they will make the standard for strangeness much smaller, like 0.001 or 0.00001. In this case, I'm going to stick with the standard of 5%. So it's usually, unless otherwise stated, use 5%. So you write, I'll put in the numbers, p-value less than 5%, then you reject H naught. So this is the general statement you use every time, and I say use 5% unless you're told otherwise. Since this is true, we reject the null hypothesis. We reject the assumption or the status quo, and instead conclude that, in words, there is evidence to suggest that the percentage, or I'm just going to say it's that less than 25%. Now I'm not going to use the result from the statistic. I'm not going to use the statistic. I'm just going to refer back to the hypothesis. There is evidence to suggest that less than 25% of people are vitamin users. And the other thing you can say is the test is significant. Whenever you reject the status quo, the test is significant and you have something to report. Sometimes that's not good. You don't want to report bad news, but in this case, I guess in this case, less than 25% of people use vitamins. I don't know, you can see that as bad news. You can see that as information nonetheless. Bad or good, doesn't matter. It's important information. So it's worth reporting because you need to update people's impressions about things, their status quo beliefs. Okay, what do you do if you don't reject? If you don't reject, we say so this is done, I finished. But note, if p-value is not smaller than alpha, we say this is not smaller than alpha, then we fail to reject. And we say there is insufficient evidence you could say against, or there's insufficient evidence that less than 25% of people use vitamins. And you can say the test is not significant. but in our case it was. So that, as I explained, is the last tool I want you to rehearse. Okay? And I've just done it for sample proportions. I have some other exercises. I have the answer completely worked out here. And then I have some, oh, my PDF isn't very nice. Let me know if you find any errors in my notes or my PDFs. Got a little bit mixed up. I guess all my notes got moved here, but that's okay. Let me go back to my drawing for a moment. So what we've calculated here is the p-value. But at what threshold would I have rejected the null hypothesis? How you know, it didn't need to be that far out. I only need to be at 5%, right? So where would I be? What should be the z-stat that gives 5% here? So in other words, this is my alpha. What is the threshold here, the critical value that corresponds to alpha? So let's see. Let's look at our tables for 5%. Notice that between here and here, we see the threshold negative 1.645, right? It's going to be the average of the two. So you only had to be negative 1.645 standard deviations below to have been considered an outlier. 95% over, 5% over there puts 95% over here. We call this the fail, let me write it in a different color. That didn't work. So this is the fail to reject region from this way over, and this is the rejection region. And I'm talking about rejecting the status quo hypothesis. Is that messy? Do you guys follow? Okay, let's see what else we have. Okay, I give an exercise here about vaccines. Okay, let's just do this one. Okay, so let me give you some time to read that. Okay, don't forget to refresh your screen if it gets blurry. Okay, one measure that is of critical importance for the practice of modern medicine is the proportion of patients that experience an adverse reaction to a vaccination. Some clinics examine every record to determine that proportion. In a large practice, though, taking a census of the records can be time-consuming. Suppose a random sample of 2,500 patients is obtained from a large clinic. Also assume that as a result of past census studies, it is known that the proportion of patients who have an adverse reaction is 1%. That's pretty high. All right, I just made this up. This is an old question. What is the approximate shape of the sampling distribution of the sample proportion? All right, so what do we have here? We have our N. And we have our P, what is known from census, right? So what is the approximate shape of the sampling distribution? P is approximately normal, P hat, the sampling distribution of the sample proportion. It's a long statement, but that refers to the symbol. That's why we use a simplifying symbol. Now compute the mean and standard deviation for this. So the mean, the distribution is approximately normal with a mean of P and a standard deviation of P1 minus P over N square root. Where did I get this from? Again, it's number 2 of the formula sheet. So I can calculate that. Actually, I'll put them right in there. Do you guys get those numbers? So don't forget, this would be 0.01 times 0.99 divided by 2500 square root. Now, using that distribution, in the spirit of SDS for p hat, find the probability that more than 2% of the patients will experience an adverse reaction. So we standardize because we have assumed, we have an approximately normal distribution, so I can use it. So this is P, this turns into a Z, and then I take that over. Everything looks like, I'll make it like a Z. So then that becomes So what is the probability that more than 2% of patients in the sample will experience an adverse reaction? Did I do something wrong here? Okay, it's because the sample, I can't speak, sorry. Because the standard deviation is so small, we're dividing by a very small number, which makes these small numbers really big. In fact, it's 5 standard deviations away. So it's a very tight distribution, around 1%. So the chance that more than 2% will experience an adverse event is 0. Let me make sure. Yeah, I did. Okay, so it's because the distribution on around the 1% is very tight, and to be even greater than 2% is very unlikely. It's 0. All right, any questions about that? All right, next part. Now we're going to do the hypothesis testing. Proponents of vaccines believe that the likelihood of an adverse reaction is very small. They actually believe it to be 0.1%. They also insist that they have evidence to support their belief. If from the large clinic 100 people out of 2,500 were found to have an adverse reaction, is there evidence against this claim of the public health officials? Okay, so this is their... We're going to try and find evidence against this status quo. I think it's a little bit unclear here, but I'm going to stick with how I have it in the solutions. And I'm going to argue that what we're doing here is we are going to have a new status quo belief. This is the status quo belief of the public health officials that believe. So this is how we do this. Always, whatever number I put here, and this has to be equals. So they believe, the status quo belief is that it's 0.001, right? And I have to put that number here as well. And then what I want to find, is there evidence against their belief? So I have to choose, is that a less than, greater than, or not equal symbol that I'm going to test? Okay, so when it says just test it, it doesn't say is it high or is it lower. You're just testing to see if it's any different. So we're just going to put a not equal sign. So this is known as a two-sided test. The one that we did before was a left-sided test. And because it's a two-sided test, you have an option. You can do it with the 5 steps that I taught you, or you can do this, you can solve it in a different way. You can make a confidence interval, and I have that written up in the notes, and we'll talk about it when we finish this. Okay, so what I've done so far is made the hypotheses, or I've made the hypothesis, null hypothesis, and alternative hypothesis statements. The next step is assume H0 is true. So that means where this is P0, that means P equals P0 equals 0.001. So we make that statement that it's true, and then let's look at the implications. If that's true, then it's also true that the sample proportion is approximately normally distributed with a mean of 0.001 and a standard deviation of that. So we need to put that together. Be careful. So that is going to be our standard deviation. And where am I getting this from? Formula 2 on the formula sheet. I always go back to the same thing and I keep repeating so you realize there's not 100 different things I'm doing. I just keep going back to the formula sheet. 0.001 times 0.999 divided by 2500 square root. 0.0006. Very small again, distribution. Very narrow, tight distribution. Small standard deviation. And next, that's the assume step. Next, you assess. Oh, I'm running out of space, so I will move that other question. So A is assess the evidence. Assess the evidence. What's the evidence? P hat from the sample is X over N. And we found out 100 people out of 2500 were found to have an adverse event. It's 0.04. All right, so before we continue, we actually have the answer already. Well, we have a hint of the answer. On my sample says it's 4%, and these are very small. So it's clearly different than that, but maybe we need to see how many standard deviations this is away from that. I think it's quite a few actually. So let's finish this, but we already have the hint that we're going to reject our null hypothesis, but we got to go through the steps. So let's do that. We used to joke about infinite chalkboards, and now it's actually possible to have an infinite whiteboard. Okay. Next step, p-value. Let's convert that oh, I didn't finish yet. This is just the p hat, so wait, I didn't finish yet. I have to get the z-score before I do anything. Let me get the z-score. So then z-stat is equal to p hat minus mean divided by the standard deviation. So it's 0.04. Assess the evidence, means standardize it. 0.001 divided 0.0006. So this is huge. .65 standard deviations above. So what does that mean? It means that the result of the sample obliterates the assumption. Like, it's so different. And again, we don't think something's wrong with our sample. We think we found evidence that something's wrong with the hypothesis. So let's see. Let's do the next step. This is the p-value step. We already know what this is too. The p-value is the probability of seeing a z-stat, or I'm going to say more generally, a test statistic as extreme or more extreme given H not true. So I write that out several times so it rings in your ears, which is important that you understand what we're doing. So now I'm going to draw this Z, and I'm going to plot my Z stat. Okay, so I take my, it's a statistic. It's computed from the sample. I take my Z stat, which is 65. Oh, I have something over there, don't I? Okay. And I'm going to plot it, and it's way over here. Oops. It's way over here, 65. And what am I going to do with it? I have to see what's the p-value, the probability of seeing a test stat as extreme or more extreme. What does extreme mean? Far away in what direction? How do I sort that out? Just like I did last time, I go back to the alternative to get the sign. I use that. So I say extreme in either direction. It's either far below or it's far above. This is a terrible thing to draw, but let me do this again. I'm going to draw it smaller. Okay. I'm going to draw it like, okay, so 65 is here and negative 65. So what I do is I plot both the Z stats down, the positive one and the negative version of it. And I see what the probability is in the tails. Now, because this is such an extreme example, it's just a bunch of zeros. The p-value here is equal to this plus this area, but they're both 0. So the point is, the chance of being out there is 0. Like, clearly, it's completely unlikely that you would have found a test statistic, or you would have found a sample result that's so extreme, unless something's wrong with your assumption. It's just not likely. Okay. So the concluding step. The concluding step is C for conclusion. You write p-value. Let me fix this. P-value less than or equal to alpha means reject H naught. So we're looking to see that the chance of seeing that statistic is small, smaller than 5% chance. Well, 0 is certainly less than 5% chance. So we do reject the null, and we conclude in the simplest way to say the test is significant and that there's evidence that the public health officials are wrong. Okay, I'm saying it in the simplest terms. They're wrong. It's not equal. So we're favoring, or we say we have evidence to reject the null. Test of significance. Something new has happened. We disagree with the officials and we have some evidence. How's everybody doing? Now the other way to compute this, the other way to solve this is suggested in the question. It says, first conduct a test of significance to test this claim, and I did that. Second, compute a 95% confidence interval around the proportion of the sample to test the claim. So we did this doing the 5 steps, the 5 HAPSI steps. I'll leave it there if you still want to look at that. The alternative for a 2-sided test, you have an option. Build a confidence interval around p hat, a 95% confidence interval in particular, using the sample result. So it's just a confidence interval. And then what we're going to do, well, let's build it and then we'll talk about it, okay? So it will be from 0.04 plus or minus 1.96. Remember, for 95% confidence, we already learned that Z star is 1.96. So I'm going to use that result. So this will be 0.04. Do I have that number already? No, I only calculated it for the P naught scenario. So I have to calculate it. So 0.04 times 0.96 divided by, let me zoom on this. That's not going to work. I'll join them. Alright, so what I want to do is compute so what I'm doing is making a confidence interval. So to make a confidence interval, we did this before. I'm going to compute the margin of error, right? That's the give or take. So 0.04 times 0.96 divided by 2500 equals square root times 1.96. So this is 0.04 plus or minus 0.0077. So I'm going to subtract that from 0.04. So I get 0.0323. I'll just leave it like that. Comma. And 0.0477. So what we've made is a confidence interval representing all the values technically in statistical terms close to or similar to p hat. And what we're going to do now is check if the hypothesized proportion falls in here. If it falls in here, then it's just as close and we haven't found anything strange. So basically we make an interval with our statistic that we calculate from the sample, and we check if the interval is anywhere near the hypothesized value. The hypothesized value, remember, is 0.001. So since P0 is not in the interval, we reject H naught. The test is significant. Wasn't that much easier? You can only do this if you have a two-sided test. Because a two-sided test tests on both sides. So you can either check in the tails if your t-stat falls away as an outlier. That's one approach. That's what we did. The other approach is to build a confidence interval and see if the hypothesized value falls in it. You can't build a confidence interval when you're not looking on both sides, okay? And the only both sides issue is when you have a two-sided test. Okay. Any questions? The answers are here. And I'll leave you to do the rest, finding the sample size. All right, it's 8 o'clock. How are you guys doing for another half an hour? Can we continue for another half hour? What I'm going to do then is go to, so I've taught you the left-sided test, the right-sided test, and I've talked about the assumptions too that we need to be doing what we're doing. That NP is greater than or equal to 10 and N times 1 minus P is greater than or equal to 10. We don't know P, right? That's the whole point of inference. So it's hard to know if that's true, so we just assume it's the case. And also we have to assume the population size is 10 times the sample size. So your sample is at least 10 times the sample size. So the sample size is just a fraction, a tenth or even smaller of the whole population. That makes all these results work. So I did all this. These are all the results, practice assignment questions, and that brings us here to inference on the mean. So I'm on page, it says here, 16. So I'm skipping over these notes because I'm trying to show you what it all means, and then you can read it easily, much more easily. So where I'm going to start are with some exercises, and in the process I'm going to talk about what confidence intervals mean. So I'm on page 18. So page 18. So what we're going to do next is the next row. Oops, moved it over. The next row in the formula sheet. We are going to talk about confidence intervals with the sample mean, confidence intervals to estimate the true mean. We're going to talk about sample size estimation and tests of significance or hypothesis testing for the mean. So what you have to do so far then is when you read a problem, identify it. Is it about the proportions? Is it about a proportion or is it about a mean? So proportion would be for an election, or the proportion of students with a certain characteristic, or the proportion of people divorced. It should say proportion, something about the proportion of units. For the average, it would talk about the average salary, average height, average income, average sales. Okay, it should be very clear, spelled out so that you know that you're in row 5 and not in row 4. So for example, we're going to look at page 18, heights. Heights of women in Canada, estimating the true or average height of all women 18 and over. The sample average is calculated to be 5 feet 4 inches or 64 inches. So that's what I'm going to use as the sample average. And the standard deviation of actual heights of women is known. So again, I mentioned it's kind of weird that we have something about the standard deviation, the true standard deviation, but we don't have about the true mean. Bear with me, it's just that we need to learn this technique, so then when I take it away, you know how to handle things. Okay, so we have x bar given to us as 64, and the true standard deviation is 2. So with that information, calculate a 95% confidence interval for the true mean of women's heights. So I'm going to take these onto a new page. So calculate a 95% confidence interval for the true mean of women's heights. So we know how to do that. For the mean, it's just like the same pattern. So it's the point estimate, the best guess of what the true mean is the sample mean. That comes from the central limit theorem In this case, did we talk about normal distribution? So there was no mention of normal distribution. We're just assuming it's normal, or we don't even have to because our size is so big. That's the central limit theorem. So we don't know about normality. If we did, we wouldn't have to appeal to the central limit theorem. But anyway, the critical value for 95% confidence interval, and then times the standard error, which by number 3 on the formula sheet is sigma over root n. In last class, I explained where that came from, and I provided you with the proof. I didn't go step by step through it, but I promised you it was an application of the rules of means and variances that derive that proof. So that's the general formula. So I'm going to do this for each case. So 64 plus or minus for a 95% confidence interval is 1.96. For a 99.7% confidence interval, you know, you want to say 3, but it's a little more precise than that. Remember those rules, that 68, 95, 99.7% rule were rounded up. In fact, for 95%, it's actually not 2 standard deviation, but very close, 1.96. What about for 99.7? We'll have to look. And we want the Z star for 99%. So let's see where we're going to find those. So this one I can get off, I just pulled off of that T table at the very bottom where the Z values are, Z scores are. Let's see if 99.7 is on that table. Because it only has a few. So 99.7 is not on this table. So what do we do when the value is not on the table? We have to go back to our first principles and use the Z table. So for 99.7 in the middle, that puts 0.15% on either side. And then I want to find this and this. So I'll begin here because that's the easiest. And I need to look inside the table for 0.0015 to see what threshold that gives me. So where do I need to be? Aha, here they are. I need to be between these 1.2965. What did I say? 2.9. I don't know. I said 1.296. 2.965. 2.965. And this one will be positive because of symmetry, 2.965. So let's put that back onto our document. So this is 2.965, and then 99% I do believe is on that, the bottom of that table. So we're going to go there. And again, you can get these in Excel. You just have to figure out how to do that. It's easier to just use this table probably. So 99% is 2.576. 2.576. So notice the more So this is the highest here, right? This is the largest confidence interval. So that means you got to be further away, right? So the area in between is the largest. You have to be further away from the mean in that case. So this is almost 3 standard deviations from the mean, which we knew. Basically, if you rounded this would be 3. But we're going to be more precise. So for the first one, that would be the first one. And you could simplify that, and I'll go through it. I want to show you the next one. And then the following one. Ah, but that's not ABC, that's ACD. What happened to B? Let's go back and look at that. This is ACD. So, to make this an interval, I have to combine the margin of error and add and subtract it. So let's do that. So you can express your answer in all these ways, but at least simplify to make the margin of error. So there's the margin of error, and then you can also make it as an interval. All right, so this is the idea, and I make an interval, and I hope I got them all right, but the solution should be there if I didn't. Okay. Something like that. Let me make sure. 515. Oh, I rounded to 2 decimal places. Anyway, something like that. So that's the 3 decimal places. All right, so that's how we do it. So we can write it like this, you can write it like this, you can write it as an interval, and you need to practice that. So I missed out on the middle one. Calculate the confidence interval that would be necessary, accurate 19 times out of 20. Notice that 19 out of 20 is equal to 95%. Actually, A and B are the same question said a different way. And some people feel more comfortable expressing it this way. That means more to people and reflects the nature of the confidence interval. So I need to talk about what is the confidence interval now. Now I argued, or I presented it as though I'm making an interval and I'm using the nature of the distribution of the sampling distribution of the sample statistic to justify the observations being, let's say, 95% around that statistic. So 95% of them being around the statistic within making it a 95% confidence interval. So what is a confidence interval then? Here's my explanation. Think about how we collect one sample, and that sample that we collect is just one of all possible samples we could have collected. So let's say we have that one sample and we've labeled the number, we listed all the numbers out, and we'll call this simple random sample A. These are the outcomes of the sample. I can calculate a mean. I could calculate a confidence interval. I could draw the confidence interval. I could say this is my confidence interval. Right? And I can go back and take another sample. I can put everybody back. If it's people or units that I'm sampling, I put them all back and I sample again. And I could get some of the same values, different values in different order. Whatever it is, here's my sample, and I've noted them with B's because they're not necessarily the same as those. I can calculate the sample mean of that sample B, and I can calculate a confidence interval. And that confidence interval, I could plot it here. So you imagine it on a number line. They should be the same interval, right? Because the margin of error is the same for each. So it's just about where the mean is, the positioning of the mean, that makes them different. So here are my confidence intervals, and I could have several. I could have, for all possible samples, I can imagine having all of these. What's our goal? Our goal is to here's a number line, and let's say the true mean is actually here. Okay, so I'm trying to get an estimate of the true mean. So this is one confidence interval where the true mean fits. Here's another confidence interval where the true mean fits. It is the case by the theory that we've developed that if you create a 95% confidence interval, what it means is that 95%, or it refers to, is that 95% of those 95% confidence intervals will actually catch mu inside. So it's the chance is that you have a confidence interval that doesn't catch mu inside. So you can imagine, I want to be more confident, I make a larger confidence interval, and with greater chance, like 99%, 99.7%, that it actually contains the true mean. But you have to be careful because you went through the trouble of collecting data and having a sample. You don't want to give an estimate that's a huge interval, right? So let's say we know women have heights on average about 64 inches. And if we're going to go through the trouble to estimate, with an interval, we don't want to say, well, she's between, women are between or the true mean average of women is likely between, 4 feet and 6 feet. Well, we already knew that. Why should we spend money on a study to do that? We already knew that. What we really want to spend money on is being precise and getting precision. So greater sample size will allow that, and we want to be sure. Usually a convention is to use a 95% confidence interval and take our chances. The chance is 5%, right? That we did not reveal the true mean, and with our interval, we didn't capture it. So those are those exercises. You can practice those. And then we get to the question of sample size estimation. So this is the second column of the formula sheet, sample size estimation. Using the information from the above exercise, what size needs to be drawn to attain an estimate of the true mean in a confidence interval that's 99% confident with a margin of error of 1? So this is like the step back, trying to find the sample size we should calculate before we actually go and make a confidence interval. So what should we do? We're going to use the same approach. We're going to take the margin of error from our formula, and I could just plop all the information in here and solve, but I'm going to take my algebra skills. I'm going to use them, and I'm going to isolate n on one side. How do I do that? Well, I cross multiply the n up, put the m down, and then square both sides. And this is really a zoom formula, right? So I have my zoom formula, but this is for means. Okay, remember the proportion, the one for proportion was n equals z star over m squared p star 1 minus p star. That's for proportions. So let's use this formula now and answer these questions. I've done that on the next page, and here we have it. So let me copy over the questions. All right, so for the first case, the confidence interval that we would estimate with that sample would be 99.7%. This is the z star for it. And margin of error of 1. So solving, we get 36 women, or 35.16 women. And my rule was, when you have to round all the way up to the next value. So we round all the way to 36. Even though it's 35.16 and you want to round down to 35, you don't do that. Because if you do that, you might make your margin of error too high on your confidence interval. And you want to restrict that for your report or your analysis or whatever it is that you're demanding that it have a margin of error 1 in your estimate. So 36 women should be sampled to achieve this precision. Now, what if we're more relaxed about the margin of error? We allow for a larger margin of error. What happens? Look, I do the same formula. I'm just going to change this 1 to a 2. So I only need 9 women then. Okay, so the more relaxed, you don't have to sample as much. The more precision, you have to sample more. And finally, what about going from the beginning, from the first one? What if I don't need to be so confident? What does that do? To reduce confidence from 99.7 to 95%, this reduces the Z star, right? Because the Z star is how many standard deviations you are away. So you're not going to be so far away, and you only need 16 women. So you can see from this formula how each of the variables influence the sample size. The larger the margin of error, no, let's say it differently. Let's say the smaller the margin of error, so the more precision, the larger the sample size. That wasn't the right one to write it on. I should write it on here because that's where it happens. No, that's not where it happens. It happens here. So I'm going to get a larger sample size here if the margin is smaller compared with this one. Obviously, the larger the confidence interval, the larger the n. So these are things you control. The Z star and the M are things you can choose. The sigma you cannot. That's given. That's just reality. The Z star and the M are up to you. Sometimes in certain industries, Z star is set to a 95%. Margin of error depends on the convention for your sector or for the kind of studying and reporting that you're doing. The margin of error is determined. So this is up to the researchers, these two. The other one is given. You can't do anything about it. All right, so now we're going to hypothesis testing. And all my drawing got screwed up here. So let me know if you have messed up drawings. Let me know. I'll send you the clean ones. I'm not sure what happened there. Okay, so I have some exercises here with the answers. Maybe I can do something different. No, I guess I'll just stick with the notes, even though they're messed up. Okay, so we're going to conduct this test. I'm going to take this information onto to a blank page. We're going to begin with a two-tailed test. Is an executive's blood pressure different from the population of males? That's my research question. The National Center for Health Statistics reports that the systolic blood pressure for males 35 to 44 years of age is normally distributed with a mean of 128 and a standard deviation in this population is 15. So when I read this, I know the distribution of just regular males, 35 to 44, that they have a normally distributed blood pressure with a mean of 128 and a standard deviation of 15. That's a given. So let's say that a sample is taken of 72 executives and we get a mean from that sample of 126.07. Now, is that different than 128? That's the question. We just want to do a test of difference. So how do we set this up? So what is the status quo? What should we believe? We should believe there's no difference, right? That is the guiding principle of the null hypothesis, that there's nothing special about executives, that is no different than other males. So we're going to set this up. Now notice what I'm doing differently here for the hypotheses is I'm using mu instead of p. I'm going to use mu instead of p, but everything else is the same. And this I will call, what I put here is mu 0. So if I believe there's no difference, the status quo, executives are no different than other regular males. Executive males are no different than regular males. Then what should this number be? No idea? Well, if they're no different, then they should also have a mean of 128. Whatever number I put here, I copy down here, okay? And then I decide what I'm going to test against. Now, this is the alternative hypothesis that I believe to be true. If H naught is rejected. And what I believe to be true is that I'm just going to look for difference, so that they're different. And these represent, this 128 represents the mean, the mu naught. So that's that. Next step. Assume H naught is true. So what do I assume, and what is the consequence? Therefore, mu is equal to mu 0, the hypothesized mean, which is equal to 128. All right, and what further is true? Then in a sample, what I know from a sample is that, well, let me write it. Since x is normal 128.15, then for the sample of 72, x bars should also be normal with a mean of 128 and a standard deviation. Remember, we have to get the new standard deviation. It's 15 over square root of sigma. No, 72. Sorry. And when you put that in your calculator, you get 1.77. So now, we can calculate the z-stat. Oh, sorry, let me finish what I'm saying and then I'll go into the next step. So what we have is the result of our assumption and our theory in rule number 3 or formula number 3. So I get to use this now only because I made a bold assumption that the null hypothesis is true. Otherwise I would be stuck. So I'm going to stick my neck out, assume it's true, and let's see. Let's now assess the evidence of the trial of the sample or experiment. It's not an experiment exactly, it's just an observational study where I assess the evidence of the study. So assess the evidence means take my real sample mean of 126.07 and standardize it, get its z-stat. So I take 126.07 and I need to minus its mean and divide by the standard deviation or the standard error. Remember, we call it standard error, but it's really the standard deviation. We just use that name when we have to put estimates inside. I'm going to keep calling it standard deviation. I think it makes more sense here. So, ready? So 126.07 minus 128 standardized gives so it's lower, it's at negative 1.09. So that's not an outlier, right? That doesn't seem like an outlier. I mean, an outlier is usually around 3 or like more than 2 standard deviations away, or some. It's further away than 1. Depends on what we set as being too far away, right? Like we have a general. Until we learned this, we were talking about 3 standard deviations being far away, but now we're being more precise, and we're going to use the standard of the level of significance of 5%, which for a 2-sided test means 2.5% on each side. So let's see. I don't think this is going to be a rejection. I think we're going to fail to reject. So let's see. Let's calculate the p-value. The p-value, I'm repeating myself, is the probability of seeing a z-stat as extreme or more extreme given H naught is true. More extreme in which direction? We go back to here and get it. We need this for our p-value. So what we do is we draw a picture. And what I do is I draw my z-stat. My z-stat is negative 1.09, z-stat negative. And then I plot also the z-stat positive. So I turn it into the positive version because I'm going to check on both sides. And I'm going to calculate the probability on the left and on the right, and then I'm going to add them together. That's my p-value. So when you have a two-sided test, I did say this before, but I need to be clear, is 2 times, it's both sides. So I look up negative 1.09 in my z table. Negative 1.09 will be over here. $13.79. So this is $13.79. But then this is also $13.79. So the p-value ends up being that the chance of being as extreme or more extreme in either direction, higher or lower, is quite high. It's going to be whatever that is times 2. %, so 0.2758. So it's not unusual that we have a mean that's 1 standard deviation away from 128 systolic blood pressure. It's not strange. There's nothing unusual. It's a 28% chance, and we specify that things will be unusual only if it's less than 5% likely, and we saw it. In this case, we're going to conclude that 0.2758 is not smaller than 0.05, so we fail to reject H naught. What does it mean? It means that there is no difference. That in male executives, according to the study, there's insufficient evidence to suggest they have a different level of blood pressure, maybe owing to the stress. That's why we were checking this, but they don't have there's no evidence they have a different level of blood pressure as the average male in their age group. So we fail to reject H naught. The test is not significant. There is no difference. I'm making short statements, but they're a little longer in the notes. All right. So that's my explanation. I'm going to stop here, and what I'm going to tell you is that for your test on the weekend, I think I'm going to keep everything on the test because the fact is that they're very related topics, and if I just let the test be different than the final, you might just focus too much on the wrong material. I need you to study all the material for the test on the weekend. So what I'm going to do is just keep going, and whatever I finish tomorrow will be on the test on the weekend and on the final. And I think I'm going to finish everything. So all I have to do next, because what I've done so far is review or introduce every topic on the formula sheet. We've done this and this and this. All that's left is the scenario where sigma is unknown. That's what I'm going to focus on tomorrow. I'm going to begin with a discussion of the t-distribution, the table, because my video for the t-distribution is defective. I don't know what happened. It's black. I'm talking to a black screen, so I need to actually reproduce that video, and I just haven't had time. So that's basically it. I just got to teach you about these two formulas, and then the other thing is the matched pairs t-test, and that's all I'm going to do. All right, so I'm going to say good night. See you tomorrow. It'll be our last class. I know it's a lot, and you should be very proud of yourself for hanging in there and sacrificing 3 weeks of your summer to get this done. So don't give up yet. Hang in there, and this is almost over. Okay, have a good night and day tomorrow. We'll see you then.